Lecture 2.14 Relativistic Momentum. So far we have only looked at kinematics, which is the description of motion without regard to the forces that cause it. We discovered that observers in relative motion perceive space and time differently as described by the Lorentz transformations. In today's lecture, we begin thinking about dynamics and the physical laws that describe objects in motion. We want to know how many of our results from classical Newtonian physics must be modified when relativity is applied. We start with the conservation of momentum. Consider the elastic collision between two particles with equal mass. If the particles collide head-on, the velocity momentum of each particle simply reverses. While nothing about this scenario gives us any reason to doubt that momentum is conserved even at relativistic speeds, it doesn't prove that our classical notion of momentum is conserved in all situations. Let's consider a slightly more general case. Sam and Sally each have a ball with mass m. Sam is standing on the ground. We'll call his frame S and we'll draw him in orange at the bottom. Sally is zooming by on a skateboard with velocity v relative to Sam. We'll call her frame S' and we'll draw her in blue at the top of the figure. In Sam's perspective in the S frame, Sam is at rest and Sally is moving to the right with velocity v. In Sally's perspective in the S' frame, Sally is at rest and Sam is moving to the left with velocity minus v. They each throw a ball along their y-axis with speed u0 as measured in their own frame. They coordinate their throws just right so that their balls bounce straight back to them after the collision. The left diagram shows what the dynamics look like from Sam's perspective on the ground. So you can see that Sam's ball moves vertically upward along the y direction in his reference frame, and Sally's takes a diagonal path because it has a horizontal component v. And the right diagram is what it looks like from Sally's perspective on her skateboard. From her perspective, her ball goes vertically downward along the y-axis, and now Sam's is the one that takes a diagonal path. The question is, what is the velocity of Sally's ball as viewed by Sam, and what is the velocity of Sam's ball as viewed by Sally? Once we know this, we can check to see if momentum is conserved in each frame of reference. To simplify things, we'll just look at the velocity of Sally's ball from each of the reference frames. We'll call the velocity of Sally's ball in her S' frame u'. It will have velocity components u' of x equals 0 and u' of y equals minus u0. Sam will measure the velocity of Sally's ball to be u in his unprimed frame. He will observe it to have an x component ux equals v, which is equal to Sally's horizontal velocity. The question is, what will the y component u sub y be? In classical Newtonian physics, we know that it'll just be minus u0, since that is the velocity that they both throw the ball at. In relativity, we must use the velocity transformation equations. So since we know u' of x and u' of y, we can use the velocity transformations to find u sub y. So we know that u' of y equals minus u0, and we also know that ux' equals 0. So therefore, u sub y is just equal to minus u0 times the square root of 1 minus v squared over c squared. Thus we find in relativity that u sub y does not equal u sub y prime. Thus we find that u sub y is not equal to u prime sub y. In fact, the magnitude of uy is less than the magnitude of u prime sub y by the factor square root of 1 minus v squared over c squared. In other words, Sam will see Sally's ball moving slower along the y prime axis than what she sees. And because we assume they threw the balls at the same speed, then Sam sees Sally's ball to be moving slower, again along the y prime axis, than his own ball. So the question is momentum conserved in special relativity? We can now answer that question by looking at the total momentum before and after the collision in Sam's frame of reference. The total momentum before the collision is the momentum of Sally's ball, let's call it P1 sub y, plus the momentum of Sam's ball, let's call it P2 sub y, before the collision. We assume the classical Newtonian expression for momentum, which is momentum is just mass times velocity. After the collision, the signs of the momentum simply reverse. Thus now Sally's ball will have a positive momentum and Sam's will have a negative momentum. So the change in the total momentum will simply be the difference between these two expressions, which we see is less than 0. Thus the answer to our question is classical Newtonian momentum conserved, and the answer is no. The question now is, what do we do? Well, we have two options. The first is we simply give up on the idea that momentum is conserved relativistically. The second option is that we redefine what we mean by momentum so that it is conserved. We'll, of course, do the latter. So in order for momentum to be conserved in the previous example, we need to define it as mass times velocity over the square root of 1 minus velocity squared over c squared. So we've defined m naught as the mass of the particle for reasons that will be clear in the next lecture. Vector u is the vector velocity of the particle in the chosen reference frame. The scalar quantity u is the magnitude of the velocity, so it's just the speed of the particle. And gamma u is the Lorentz factor associated with the particle's velocity u. In future calculations, we'll have many velocities flying around, and so sometimes it's helpful to keep track of which velocity is appropriate for a particular gamma term. So that's why we've written the subscript u on the Lorentz term. So we see that the relativistic momentum is simply equal to our normal classical Newtonian momentum multiplied by the gamma factor. Here's a plot of the momentum divided by the mass of the particle, i.e. the velocity u over the square root of 1 minus u squared over c squared. We see that in the classical limit, when u is much less than c, the momentum per unit mass is proportional to the velocity, just like we would expect in classical physics, when momentum is just mass times the velocity. As the momentum approaches the speed of light, the momentum per unit mass diverges to infinity. As we will see later, this is partly why faster than light travel is impossible, because of divergences when quantities approach the speed of light. So finally, let's show that our new definition of momentum satisfies momentum conservation in the example that we've been discussing. So again, we're calling the momentum of Sally's ball in Sam's frame of reference p sub 1, and the momentum of Sam's ball in his own frame of reference p sub 2, so unprimed coordinates. So the momentum of Sam's ball is P2 sub y equals m naught u naught over the square root of 1 minus u naught squared over c squared. Let's now write down the y component of the momentum of Sally's ball as seen by Sam. So notice that the velocity in the numerator is the y component of Sally's ball as seen by Sam, and the velocity in the square root term in the denominator is the square of the total speed. So it depends on all of the vector components of the velocity. So we plug in that u1x equals v, and u1y equals u naught times the square root of 1 minus v squared over c squared, and then we square each of those terms. So we can factor out a 1 minus v squared over c squared out of the bottom term. The square root of 1 minus v squared over c squared term in the numerator cancels the term in the denominator. We find that p1y equals minus m naught u naught over the square root of 1 minus u naught squared over c squared. Thus we find that p1y equals p2y, just with a negative sign. So with our relativistic definition of momentum, we see that the y component of the momentum of Sally's ball is just equal to negative the y component of Sam's ball. So when we add them together, the total momentum of the system is going to be 0, and after they bounce off of each other, the total momentum will stay 0 and momentum will be conserved. Okay, up next we will talk about relativity and Newton's laws.